Okay, so quite an important principle in physics is the principle of conservation of energy. So the conservation of energy in physics says that energy cannot be created or destroyed, but it can be transferred between stores. So that's a really important thing in physics. You can't create energy, you can't just magic it out of thin air, and you can't destroy it either. You can't get rid of it. You can only transfer it. Okay? Okay, and whether that energy is transferred usefully or dissipated into the surroundings, it doesn't matter. All of the energy you put into this will come out of the other side, either as useful energy or dissipated into the surroundings. I've got an example here. This is a pendulum. So a pendulum basically swings, and this particular pendulum is going to swing from position A through position B and then up to position C, and then it will swing back again through B and then to A, and so on. It will just keep repeating. Now, if I give the pendulum some gravitational potential energy, I can lift it up, and that's what I'm doing at position A. I've given it some gravitational potential energy. So this here has got maximum gravitational potential energy. And then as it starts to swing, it will gather some speed, it will gather kinetic energy. Okay, and at position B is going to have maximum kinetic energy. That gravitational potential energy at A is going to be transferred to kinetic energy at B. And then at position C, it's going to be transferred back to potential energy, gravitational potential energy. And then it will reverse, it will go back through to kinetic energy and then potential energy. Some of that energy might be dissipated into the surroundings as it experiences air resistance, and also at the top here, where the pendulum meets the ceiling, there might be some heating effect or something like that where it dissipates it into the surroundings. So if I lift the pendulum 0.5 meters, let's give the pendulum a mass. Let's give it a mass of 2 kilograms. Okay, so if the pendulum has a mass of 2 kilograms, I can figure out how much gravitational potential energy I give it to get it to A. So I'm lifting it 0.5 meters. We can use this equation. Gravitational potential energy is equal to mass times gravitational field strength times by the height that I've lifted it. So mass is 2g. I'm going to assume at the top here, I'm going to assume it's 10 just to make it easy. And then times that by the height, which is 2. So that's 2 times 10, which is 20, times by 2, which is 40 joules. Okay, now if we assume an absolutely perfect system, we can now at this point work out the kinetic energy at B. Okay, we can work out the kinetic energy at B. In a perfect system, the kinetic energy at B is going to be the same as the potential energy at A, because remember, energy can't be created or destroyed, only transferred, and assuming 100% efficiency, it's all going to be transferred into kinetic energy. Okay, so this is also going to be 40 joules. We could actually work out the speed as well. We could work out the speed that it's moving through that point using the kinetic energy equation. Kinetic energy is half times the mass times the velocity squared. Okay, if we rearrange it, we can say 2 times the kinetic energy is equal to mv, just by mv squared, just by removing that half and moving it to the other side. We can also then divide it by m, 2ek divided by m, we end up with v squared. If we want to get rid of that v squared, we can just simply move, we can just do the square root here. So if you wanted to work it out, you could just plug in the mass, which is 2 kilograms at the bottom there, 2 times by the kinetic energy, which is 40, divided by the mass, which was 2 kilograms, square root it, and whatever you get from that equation, I haven't got a calculator to hand, but whatever you get to that from that equation, you get as your velocity. Okay, right, now here's a second one you can have a go at. Okay, so a 5 kilogram brick is dropped from a height of 20 meters. Calculate its velocity as it hits the ground, assuming that g is equal to 10 newtons per kilogram. Okay, now you don't actually need to know the mass of the brick. Okay, you don't need to know the mass of the brick, it doesn't matter, but I've put it in there anyway just in case you want to use it. I will go through the answer. I'll pause the video, I'll go through the answer when you've unpaused it. Okay, let's go through it then. So firstly, we need to figure out how much gravitational potential energy it has at 20 meters height. So gravitational potential energy is equal to mass times gravitational field strength times by the height. Okay, so the mass is 5, gravitational field strength is 10, and height is 20 meters. Okay, so 5 times 10 times 20 gives you 1,000 joules. Okay, so it's got 1,000 joules of gravitational potential energy. Now, when it hits the ground, assuming that there's no air resistance at all, then all of that gravitational potential energy will be transferred into kinetic energy. So we can make that equal to 1,000 as well. Okay, now to work out the velocity, we need to rearrange the kinetic energy equation, half mv squared. So we can times both sides by 2 to get rid of the half, so 2ek, and we can also divide both sides by m, and then we end up with v, that equal to v squared to get rid of the m. Now, if you want to get rid of that squared sign, you can just square root both sides. So 2ek over m equals v. Okay, so let's plug the numbers into this equation. So we've got 2 times by 1,000 divided by the mass, which is 5 kilograms, and then square root the whole thing. You end up with, and I do have a calculator this time, okay, you end up with 20 meters per second of velocity. Okay, now remember, I also said that you don't actually need to know the mass, and this is why. Let me show you why. We know that energy can't be created or destroyed, it can only be transferred. So we're going to assume that all of the gravitational potential energy that we put into it is transferred to kinetic energy. Okay, so they're both the same. Yeah, gravitational potential energy is equal to mgh, and kinetic energy is half mv squared. What we can do is divide both sides by m. If we divide both sides by m, we get rid of the m on both sides. So we've no longer got mass involved at all in our equation. So our new equation is gh equals half times v squared. Okay, so let's simplify it further. So we can times both sides by 2, so we get 2gh equals v squared, and we can get rid of the square root by squaring both sides, square rooting both sides. 2gh is equal to v. There we go. Okay, and you can plug the same numbers into the equation. You get 2 times gravitational field strength, which is 10, times by the height, which was 20. Okay, and you get the same answer, 20 meters per second. Okay, so that's two ways of doing this equation. You can either do it the easier but slightly longer way, or you could just do it if you're good at maths and you might want to do it this way. Just remember that all of the gravitational potential energy you put in will come back out again as kinetic energy. Now, in reality, it's important that you know that actually some of it will be dissipated into the surroundings. That doesn't violate the conservation of energy principle, because the energy is still coming out, but it's instead of going into kinetic energy, it's being dissipated into the surroundings. Okay, that's the end of this video. I will see you in the next one.